Hello and welcome back to the deep dive. Today, we are not just, reading about chemistry. We are virtually stepping right into the laboratory.
Mm-hmm.
And I want to start by asking you to trigger a specific sense memory. Just close your eyes for a second. Imagine you're in the kitchen and you open a bottle of vinegar. You know that sharp, stinging smell?
Oh, that intense sour scent. Yes, the one that sort of hits the back of your throat.
Exactly.
Mhm.
That is the smell of acetic acid. And today, our mission is to find out exactly how to build that molecule, pretty much from scratch.
Right.
We're diving deep into Unit 8, aldehydes, ketones, and carboxylic acids, and we're focusing specifically on the methods of preparation of carboxylic acids.
And I'm very glad we're spending time on this. You see, for a lot of Class 12 students, this unit just feels like a huge amount of memorization.
Yes.
You open the textbook, you see a list of 6 or 7 reactions, and you just think, okay, I have to learn this, but that's not the full story.
Right. Our sources today suggested if you understand the logic behind it, the why, then the memorization part, it almost disappears.
It really does.
So let's start with that mission. Why should we care so much about making these acids in the first place?
Because they're chemically powerful. We are trying to turn simple molecules like alcohols into these robust acidic powerhouses.
So they're the final form, in a way.
Exactly. Carboxylic acids are the end game of oxidation.
Yeah.
They're used in everything from food preservatives to making pharmaceuticals. If you know how to synthesize them, you basically hold the keys to organic construction.
Okay, so we're building powerhouses. Let's look at the how. The notes describe a concept called the oxidation ladder. This seems to be the core idea.
It is the core idea. Think of oxidation not just as a reaction, but as a direction. Imagine a ladder.
Okay, I have the ladder in my mind.
The ground underneath is your simple hydrocarbon, an alkene, just carbon and hydrogen.
No oxygen at all.
None.
Hmm.
Now, you step onto the first rung. You add 1 oxygen bond. That's an alcohol.
Simple enough. Alcohol is rung number 1.
Correct. Now, you climb 1 more rung, you lose some hydrogen, you form a C double bond O, that's your aldehyde, you're higher up the oxidation scale.
And the very top of the ladder.
That is the carboxylic acid. It's the penthouse. You have 3 bonds to oxygen on that 1 carbon. You can't really go any higher without breaking the whole chain.
So preparation is just the art of pushing molecules up this ladder?
Precisely. We use chemical tools, oxidizing agents, to shove them up. At the particle level, what's really happening is we're breaking CH bonds and forming CO bonds. The whole goal is to build that specific COH functional group.
Okay, that makes perfect sense for the oxidation method. But looking at our sources, that's not the only way to get there, is it?
No, it's the most common, but there are other paths, other highways, if you will.
So let's get the main definition down first, the anchor definition for the exam.
Right. Carboxylic acids are prepared primarily by the oxidation of primary alcohols, aldehydes, or alkylbenzenes, by hydrolysis of nitriles or esters, or by carboxylation of Grignard reagents.
Okay, 3 main highways then. Oxidation, hydrolysis, and carboxylation.
That's it.
Stick with highway 1.
Yeah.
Oxidation. This seems to be where the big trap is for students.
It is. This is where exams will try to trick you.
The notes mention a misunderstanding trigger about alcohols. I want to clear this up right away.
Great.
So the logic goes, if I have a primary alcohol, I can oxidize it all the way to an acid.
Correct.
But if I have a secondary alcohol, I can oxidize it. But it stops. It doesn't go to an acid.
That's absolutely correct. It stops at the ketone.
But why? I mean, if you're just adding oxygen and removing hydrogen, why does the secondary alcohol hit a ceiling?
This is the #1 conceptual error. It comes down to structural real estate. To become a carboxylic acid, the carbon atom needs to form 3 bonds with oxygen.
Okay.
A primary alcohol has its functional carbon attached to only 1 other carbon. That means it has 2 hydrogens available on it. It has room to make those bonds.
It has spare parts it can trade away.
Exactly.
Yeah.
Now look at a secondary alcohol. That functional carbon is sandwiched between 2 other carbons. It only has 1 hydrogen attached. You can remove that 1 hydrogen to make a ketone, to make the CO double bond. But then you're stuck.
You've run out of hydrogens to remove from that carbon.
Yes. To oxidize it further, you'd have to break a very strong carbon-carbon bond, which requires really harsh conditions that usually just destroy the molecule.
So the rule is, primary goes all the way to the top floor, secondary gets stuck on the 2nd floor at the ketone.
Perfect way to put it. It's a crucial distinction. I see students lose marks on this all the time.
Okay, now let's visualize this. The notes have a section called the mental movie, which I think is great for making this stick.
I agree. Visualizing it is better than just memorizing equations.
So listeners, I want you to picture a lab bench. On it, there are 3 glass vessels. Let's start with vessel number 1. This is our oxidation path.
Inside that vessel, you have a clear liquid. That's your primary alcohol. Now you're going to pour in the oxidizer. Let's use potassium dichromate. It's a bright, vivid orange liquid.
Like a strong orange squash.
A bit darker, yeah. More like rust-colored water. You mix them, you start heating, and now you just watch the color.
What happens?
As the reaction happens, that orange fades, it starts to turn murky, and then it settles into a deep green color.
Just orange to green, that's the signal that it's worked.
It's the visual proof. Or if you use potassium permanganate, you'd see the famous purple fade.
Ah, I remember that from the lab.
It starts as a deep royal purple, and as it oxidizes the alcohol, the purple just vanishes. It becomes colorless.
And what about the smell?
That's the best part. It starts smelling like surgical spirit. That's the alcohol. Then you might get a brief, sharp, pungent smell. That's the aldehyde intermediate.
And
Finally, it settles into that familiar, sour, vinegar-like smell that tells you, I have arrived, I've made the acid.
That's a very vivid picture. Okay, let's move to vessel number 2, the Grignard path. The notes call this the welding line.
This one is my favorite. It's so clever. In oxidation, you're just changing the group on a chain that already exists.
Right.
But the Grignard method, it actually changes the carbon skeleton of the molecule. You make the chain longer.
And this is where we use dry ice, correct?
Yes. So imagine vessel 2. You have your Grignard reagent, say methyl magnesium bromide, dissolved in dry ether. It has to be completely dry.
Why is that so important?
Because Grignard reagents are destroyed by water. If even a drop of moisture gets in, it just turns your reagent back into a simple alkane. The reaction fails.
Okay, so bone dry, then you add a chunk of dry ice, solid CO2.
You drop it in, and the reaction is not subtle. It fizzes vigorously.
I can imagine.
You see this bubbling mixture, and as it reacts, a solid white salt starts to form and precipitate out. That's the magnesium salt of your carboxylic acid.
But it's not the acid yet?
Not yet. It's the salt. Now, and only now, you add water with a bit of acid, and that white solid dissolves, and you're left with your pure liquid carboxylic acid.
So dry ice plus Grignard equals acid. But there's a trap here too, isn't there? A counting trap.
The carbon count trap. This is so critical for exams.
Explain it.
Okay, let's say you start with a Grignard reagent that has 2 carbons, an ethyl group. You react it with CO2. How many carbons does the CO2 molecule have?
1.
So 2 plus 1 equals?
3.
Exactly. Your product will be propanoic acid, which has 3 carbons. Students often forget to count the carbon from the CO2. They see ethyl and they write ethanoic acid.
And they get 0 marks.
0 marks. You have to remember, the Grignard method grows the chain by 1 carbon.
So oxidation changes the group, Grignard grows the chain.
A perfect summary.
Let's quickly look at vessel number 3, the nitrile path. This one feels a bit quieter.
It is less dramatic, but it's very reliable. Nitriles are compounds with a carbon-nitrogen triple bond, the CN group.
And we want to turn that CN into COH.
Right. We do this by hydrolysis. Hydro for water, lysis for breaking. We use water to break that triple bond.
So what does that look like?
In your mind's eye, see a flask with a nitrile solution. It's colorless. You add water and a catalyst, maybe an acid, and you heat it. It's a slow simmer.
Just boiling it.
Yes. And as it boils, water molecules are attacking that CN bond. First, it becomes an amide, but you keep boiling. Eventually, the nitrogen gets kicked out entirely as ammonia gas.
And ammonia has a very distinct smell.
It does, that pungent cleaning fluid smell. If you smell ammonia coming off, you know the nitrogen is leaving and oxygen is taking its place to form the acid.
So the 3 movies. Vessel 1, the color change of oxidation. Vessel 2, the fizzing dry ice of Grignard. And Vessel 3, the ammonia smell from nitrile hydrolysis.
If you can hold those 3 images in your head, you've got 90% of the preparation questions covered.
Now, I want to pivot to a real-world example from the notes. We talked about aspirin, probably the most famous carboxylic acid derivative in the world.
Acetylsalicylic acid, yes.
The manufacturing of aspirin actually uses a version of these methods, doesn't it?
It does. To make aspirin, you first need salicylic acid. And one of the classic ways to make salicylic acid is to take a phenol derivative and add CO2 to it under pressure.
Wait, that sounds familiar. That's the welding concept again?
Exactly. It's called the Kolbe-Schmidt reaction. But the logic is identical to the Grignard reaction.
Yeah.
You are taking a carbon ring and literally welding a CO2 molecule onto it to create the COOH group.
It's amazing to think that when you take a pill for a headache, you're swallowing the result of a chemist playing with molecular Lego.
That is exactly what organic synthesis is. It's architecture on a nanoscale.
Okay, before we wrap up, I want to do a quick stress test.
Yeah.
I want the exam-safe clarity lines. I'll throw a scenario at you, and you give me the absolute cheat sheet rule.
Get ready.
Scenario 1, I have a secondary alcohol. I heat it with strong KMNO4. What do I write as the product?
You write a ketone. Do not write carboxylic acid. End of story.
Scenario 2, I have toluene, which is a benzene ring with a single methyl group. I boil it with KMNO4. What happens?
That entire methyl group gets oxidized all the way down to a carboxylic acid group. The side chain gets burned off, leaving a COH group on the ring. You get benzoic acid.
And what if the chain is longer, like propylbenzene?
Doesn't matter. Even if it's a long chain, the strong oxidizer cuts it off right after the first carbon and turns that one carbon into COH. It's a very common exam question.
Okay, last one. Scenario 3. I need to convert methyl chloride, which has 1 carbon, into ethanoic acid, which has 2.
The carbon count increased.
Right.
So you cannot use simple oxidation. You have to use a method that adds a carbon. That means either the Grignard method or the nitrile method.
That's the key insight. Count the carbons first.
But always. It dictates your entire strategy.
Okay, we have climbed the ladder, we have welded CO2, and we have boiled off ammonia. To help our listeners package this all up, you have a mnemonic, OX-S-ANA.
Yes, just keep the map clear.
Break it down for us.
OX stands for oxidation. That's your primary alcohols, your aldehydes, the burning path.
Got it. OX.
S stands for synthesis with Grignard. Remember, synthesis implies building up, adding that extra carbon. OS. O is for organic hydrolysis, the water path for nitriles and esters.
And the N.
N is the big warning sign. No secondary alcohols. Just remind yourself one last time, they stop at ketones.
OX and N. Oxidation, synthesis Grignard, organic hydrolysis, and no secondary alcohols.
That is a brilliant little pocket tool.
It covers all the main routes.
As we close, I want to go back to that ladder image. We started with the smell of vinegar, and it's easy to think of these as just chemicals in a jar, but that ladder connects them.
It does. It shows that an alcohol, an aldehyde, and an acid aren't strangers. They're family, just at different stages of oxidation. You're just helping them grow up.
And mastering this isn't just about the exam. These are the tools used to make medicines, materials, and even flavors. Absolutely. Every time you see benzoic acid in a food preservative or citric acid in a drink, remember, a chemist had to climb that oxidation ladder to put it there.
Well, that brings us to the end of this deep dive.
Yeah.
To all the students listening, draw the ladder. Picture the 3 vessels. If you can see it, you can solve it.
Keep practicing those conversions. You've got this.
Thanks for listening. We will see you on the next deep dive.